We continue to examine special methods for finding particular solutions for a linear non-homogeneous ODE. And first, we introduced the so-called method of undetermined coefficients. Now, we introduce another method, which is known as the method of variation of parameters. So again, as we stated in the previous lectures, this is a method to find a particular solution for a linear ODE, linear non-homogeneous ODE. Okay? Recall to find a particular solution for a linear non-homogeneous ODE. This is a method. Okay? So what is the difference between the method of undetermined coefficients and the method of variation of parameters? We stated the difference between them. However, let us remind once again, the method of variation of parameters is much more generally applicable in the sense that we can apply it to a non-homogeneous linear ODE with variable coefficients as well. And second, there is no restriction on the non-homogeneity term. Okay? In the method of undetermined coefficients, a systematic procedure to find the candidate solution can be accomplished only when the right-hand side itself satisfies a homogeneous ODE with constant coefficients. However, there is no restriction on the non-homogeneity term in the method of variation of parameters. Good? But, of course, we assume that the main restriction, or main assumption is that the homogeneous solution is known. In other words, the fundamental set of solutions is known. In other words, the set of linearly independent solutions of the corresponding homogeneous equation is known. Okay? So look, we apply the method for finding a particular solutions for this equation in principle. So no restriction on the coefficients. So coefficient functions may be functions of t. So in principle, the method of variation of parameters may be applied to such an equations. S and f of t, no restriction of f. Just, of course, from the existence uniqueness theorem, we require that there is a t interval in which f is continuous to assure that there is a solution, right? That's enough. Okay, look, in fact, the method of variation of parameters has been introduced previously in finding a particular solution for the systems of first order ODEs. Okay? So recall that such an equation, let's say 1, this equation has a system representation. I mean, a system of n linear first order ODE. A system of n linear first order ODEs. Okay? Has a system representation of the form. Look, x prime is x plus b of t. Good. Where b of t is a vector function representing the non-homogeneity term, which has all 0 and 3 except the last one, and the last one is f of t. Also, we know the form of A, in that case, not important, and x of t is a function, is a vector valued function with components x1, x2, xn of t. Okay? And what is also known, we know that x1 of t, the first component function, is nothing but y of t. Good, this is very well known. And also we know that x2 of t is y prime of t. Good, and so on. xn of t is yn minus first t. Good. So this is the link between 1 and 2. Okay, and we assume that homogeneous solution of 2 is known. Recall X homogeneous, the solution of the corresponding homogeneous system, has the form okay, where C is a fundamental matrix, and in this case, fundamental matrix has the form y1, y2, yn, y1 prime, y2 prime, yn prime. Okay? Continuing in this way, here is yn n minus first t. Good. In fact, this is x1 prime, or x2, so on. Here is another solution. This is x1. This is its solution, and so on. So when we consider the system representation of the nth order ODE, a fundamental matrix looks like that. And this fundamental matrix satisfies such that itself, this matrix satisfies the matrix equation C Good. Say 3. Okay. And what about C in this homogeneous solution? C is the vector containing arbitrary constants. Good. Now, we propose, look, we then propose a solution of the type. I'm trying to remind you the method, what we call it, the variation of parameters, which is used to find particular solution for a system of n first order ODE. Okay? We propose a solution like C of t, u of t. Good. Say 4. Good. Well, let us denote this by 3 and this by 4. Hence, this becomes 5. Where u is a vector function with components u1, u2, un is a vector function to be determined. Good. So compare this solution and the solution in 3. Look, in place of the constant vector, or the vector whose components are all constants, not depending on t, okay? It is replaced by a vector function whose components vary with t. So components are varying functions of t. This is why we call this method the method of variation of parameters. In a sense, I'm going to show that there is a particular solution of this type, okay? So in a sense, looking at the homogeneous solution, yes, the constant vector has been replaced by a vector whose components are changing with t. The method is called variation of parameters. What is the idea? Now, if this is a solution, it must satisfy the non-homogeneous equation, non-homogeneous system in 2. So if 5 is a solution, it must satisfy the system in 2. That is, let's take its derivative. Look, its derivative, what is the derivative of that vector function? Be careful, the order of matrix vector should be careful. We use the ordinary product rule differentiation with the care of the order, because this is a matrix times vector, so it makes sense in this order. Otherwise, u multiplied by psi is even undefined, okay? Or maybe undefined. So psi of t u, then psi u prime t. Good. So let us substitute into the system in 2. So the derivative is psi prime. I'm not going to write the variable t for symbol economy, but be careful, these are functions of t, psi prime u plus psi, and wavy line under the symbol, recall that, implies that the corresponding quantity is either a vector or a matrix quantity. Okay? The bold-face type letters in your textbook, okay? Implying or giving vector and matrix valued quantities. Plus psi u prime, okay? This is the derivative on the left-hand side. Right-hand side is a times x. So a times x, x is psi u plus b of t. Good? So the equation must be satisfied. So please be careful, or this system may be written as consider the terms which are multiplied by the vector u, this and this. So we have psi prime minus a psi, this matrix, multiplied by u, and which remains then psi u prime must be b of t. Good? So please be careful. I say that from 4, look at 4, psi prime is a psi. So psi prime is a psi. So this is the 0 matrix. So this term vanishes, and it gives us that psi u prime must be b of t. So there is a matrix of order n, a matrix of order n, and a vector which contains the derivatives of these unknown functions proposed in the solution must be equal to b, and b is very well known. Okay? It is a non-homogeneity term, non-homogeneity vector function. And when it characterized an nth order linear differential equation, components are all 0. Please be careful, this is 0. Components are all 0 except the last one, which is f of t. Good? So we saw, because psi is a fundamental matrix, columns are linearly independent vectors, and therefore it is invertible. So in principle, you can find its inverse. Okay? Psi is invertible. So u prime, but this is important, let's say 6. So formally, u prime vector is psi inverse b. Okay? This is true because psi is a fundamental matrix. So it is invertible. So formally look, we get u prime, not u. I say that the proposed solution, vector solution, has this form. So we assume that the fundamental matrix is known, that this homogeneous solution is known. So our objective is to find u. And we see that if u prime satisfies this system, not u itself, but the derivative of vector u satisfies this system, then this vector in 5 becomes indeed a solution of the non-homogeneous equation because it satisfies the system upon substitution. And in principle, the derivative of u exists uniquely because psi is invertible, and therefore this is a linear system of n equation. You can find u prime, not the vector u, but the vector which contains the derivatives of the components u1, u2, un can be determined uniquely, okay? And therefore, we get this solution. And this is indeed a solution. Formally, look, taking the integral of both sides to get u of t becomes this integral psi inverse. Now, recall that these are functions of t. If you want, you can introduce a constant, arbitrary constant vector. And now, recall the type of the solution. What is x? Multiply throughout by psi from the left, okay? You get the solution. So the solution looks like this. Psi of t, this integral psi inverse, b of t dt plus psi of t c. Good? So formally, the solution looks like that. This is a very well-known formula which has been derived previously. Now, the interpretation of this vector function is important. Psi c, what is that? It is the homogeneous solution. Look. Homogeneous solution, that is the solution of the corresponding homogeneous system. Good? And therefore, this part represents formally a particular solution. A particular solution of the system. Okay? Now, what is the link? So this is important. U prime b of t, we get u prime from this system. So then integrating each coefficient function, each component function, we get u1, u2, and un, which appears in the proposed solution. Okay? So now, when we have this system representation, remember that returning back to this single equation and keeping in mind that x1, the first component function, is y. Now, the solution now let us find the link between that vector solution and now from the solution in 5. Okay? The vector solution x1 of t, x2 of t, xn of t, good, is written as a fundamental matrix times u, and fundamental matrix, if the system is the system representation of the single linear ODE of order n, has these first column yn of t, so on, and here we have u1 of t, u2 of t, un of t. And since we need to find only x1, which is y, okay? Recall that x1 of t in the system representation is nothing but the required solution. So we need to find just x1 of t. So performing this matrix and vector product, from which x1 of t is y1 of t u1 plus y2 of t u2 plus yn of t un of t. And this x1 is nothing but y. So particular solution, so according to the method of variation of parameters, okay, we propose a solution of the type, look, y of t, y1 of t, u1, y2 of t, u2, and yn of t, un of t. Good? And recall that homogeneous, recall the solution of the corresponding homogeneous ODE. It is like that. y1 of t, c1, y2 of t, c2, yn of t, cn, or written in the other order, c1, y1, c2, y2, cn, yn. So as you see, the same idea is true. So this solution, which is proposed to be a particular solution, contains, in place of fixed arbitrary constant c1, c2, cn, we have varying functions of t. So our method is called the variation of parameters, or the method of variation of parameters. So how can we find u1, u2, un? We, not u1, u2, un directly, but their derivative can be determined from this system. And the derivatives of u1, u2, un may be determined by the algebraic system. Which system? Recall C of t u prime is b of t. Good? So this is the system. Remember C, a fundamental matrix has that form, y2 of t, yn of t, okay, y1 prime of t, yn prime of t, y1 prime, y2 prime, and finally y1 n minus first derivative of t, yn n minus first derivative of t, times u prime, so u1 prime, u2 prime, un prime must be equal to b of t, has this form, 0, 0, 0, and finally f of t. So we solve this system for u1 prime, u2 prime, un prime, and then integrate these functions to get u1, u2, un, which appears in the solution. Note that there is no restriction on f of t in this procedure, and the equation may be an equation with variable coefficients or constant coefficients. Only thing which remains, which must be known, is the fundamental set of solutions. Yes, a fundamental set of solutions, that is a fundamental metric solution for the corresponding system. So this means that all n linearly independent solutions are very well known. Provided that these are known, okay, we can apply this procedure to find a particular solution, okay, of this type. Anyway, so the system, this is in the second order case. Look, let's illustrate the procedure in the second order case. So let's say in the case of a second order linear ODE, linear non-homogeneous ODE, that is, we consider, please be careful, the differential equation should be considered in its reduced form. So highest derivative term, in this case second order term, is the highest derivative, should have unit coefficient plus a 1 of t y prime plus a 2 of t y is f of t. Okay? So we propose this solution, y1 of t, u1 of t, plus y2 of t, u2 of t. So the combination of two solutions. Okay? Now, what we assume, so fundamental set of solutions contain just y1 and y2. Two solutions in this case. So a fundamental matrix is of the form y1 of t, y2 of t, y1 prime of t, y2 prime of t, where, look, psi u prime is this vector, 0 f of t. Okay? Or explicitly, y1 of t, y2 of t, y1 prime of t, y2 prime of t. Look, we find not u1 and u2, but they are derivatives by solving this algebraic system, and then integration of u1 prime and u2 prime. We have this system, 0 f of t to solve. So this is an algebraic system which has a unique solution for u1 prime and u2 prime, because since the coefficient matrix matrix of the system is nothing but a fundamental matrix. With determinant psi is this one, y1, y2, y1 prime, y2 prime, non-zero. Okay? For t in the alpha beta t interval where the coefficient functions are continuous. Okay? And this is known. y1, y2 are known, so their derivatives may be obtained easily. So this system is a system of two equations in two unknowns. How can we solve it? By Cramer's rule. For example, you may use Cramer's rule, or simple elimination procedure may be used to solve u1 prime and u2 prime. Or by Cramer's rule, everybody knows the Cramer's rule, I guess. So look, we have omega, okay, which is this determinant. What is it? So let's write it explicitly. y1, y2 prime minus y1 prime, y2, okay? By Cramer's rule, we also find the determinant of another matrix, omega 1, which is the determinant of this matrix, 0 f of t. Okay? First column of fundamental matrix is replaced by the right-hand side column vector, and the second column of the fundamental matrix remains unchanged, y2 prime. So this is minus y2 f of t, and omega 2 is the determinant of this matrix. Which matrix? y1, y1 prime, 0 f of t. So omega 2 is the determinant of the matrix, where the second column of fundamental matrix, which is the coefficient matrix in this algebraic system, has been replaced by the right-hand side vector function, which is simply y1 times f of t. Then u1 prime is what? Omega 1 over omega. And u2 prime is omega 2 over omega. Okay? Or you may solve this system using two equations. We have two equations in two unknowns. Okay? First equation is this: y1 u1 prime, y2 u2 prime is 0. Okay? By elimination method, you can solve this system. Second equation is y1 prime u1 prime plus y2 prime u2 prime is f. So two equations in two unknowns. Unknowns are u1 and u2. Hence, u1 prime and u2 prime. Remember that y1 is very well known. y2 is very well known. They are two linearly independent solutions of the corresponding homogeneous system, homogeneous equation. And we assume, and this is basic to the to the variation of parameters, to the method of variation of parameters, that the solution of corresponding homogeneous equation is known, which means that y1 and y2 are known. So their derivatives are also known, or may be calculated. So the f is very well known. It is the right-hand side non-homogeneity term. Okay? So we find u1 prime, u2 prime using Cramer's rule or a simple elimination procedure. Then integrating, okay? So look, it is not important to memorize the formulas, but look, if you want, for the second order case, of course, in the case of a third order ODE, we get a system which contains three equations in three unknowns. A similar system which contains, whose coefficient matrix is of order 3. Okay. So look, from that solution, so we find that u1 prime is omega 1 over omega. Omega 1 was y2 of t f of t over omega was that y1, y2 prime minus y1 prime, y2. Or let's write it, it's in this form, omega y1, y2 of t. Okay? So on integrating, we get u1 of t, this integral, y2 f of t over Wronskian determinant of y1 and y2, which is a function of t, dt. If you want, you can introduce arbitrary integrating constants. u1 prime is with a minus sign, yes, do not forget this minus sign, minus y2 times f of t, okay? And u2 prime of t is y1 of t f of t over the determinant of the coefficient matrix, which is nothing but the coefficient matrix y1, y2 of t. Okay. Do not forget this minus sign for u1 prime. Therefore, u2 prime results in this integral y1 f over omega y1 y2 of t dt plus perhaps an arbitrary integration constant. Okay? So recall the solution we propose. So recall that we propose this solution y1 u1 plus y2 u2 of t, hence the solution. We get this one, c1 times y1, okay, plus c2 times y2 plus y1 times this integral minus y2 f over Wronskian determinant dt, good, plus y2 times this integral term y1 f over omega dt, good. So if C1 and C2, if you introduce arbitrary integration constant, you generate the general solution. This is nothing but the homogeneous solution, which is very well known. So since we are interested in a particular solution, in fact, where a particular solution looks like this one. Okay? y1 of t, and this integral minus y2 of t f of t over Wronskian determinant of y1, y2 dt plus y2 of t and this integral y1 f Wronskian determinant dt. Okay? Now, in fact, it is unnecessary to memorize any formulas, but you have to keep in mind that we propose a solution of this form for finding a particular solution of a second order ODE where the two solutions y1 and y2 of the corresponding homogeneous equation are known. Two linearly independent solutions of the corresponding homogeneous equation should be known. Okay? So y1 and y2 are known, so u1 and u2 have to be determined. And if you have an equation of order 3, add one more term, y3 of t plus u3 of t. Okay? When you are dealing with a third order ODE instead of a second order ODE, the form of a particular solution we must propose may be extended in a straightforward manner, adding just this term, y3, u3. Okay? So in general, it contains n terms. Good? Now, let us solve a few examples and finish without memorizing any formula, just you keeping in mind that a proposed solution should be of the form y1 u1 plus y2 u2 and so on. And the derivative of u1 and u2 can be determined by an algebraic system where the coefficient matrix is nothing but a fundamental matrix, and the right-hand side is a vector with only one non-zero component function, which is the last one, and it is f of t. Look. So the ODE. Which one? Let's find a good example. Here is an example. Y double prime to y prime plus y is e to power minus t over t. Now, look, the equation, observe that the ODE is a second order one with constant coefficients. So for a moment, you may think incorrectly that you may apply the method of undetermined coefficients, but you can't because of the right-hand side. Recall that there is a restriction if you want to use, in principle, because the equation is an equation with very constant coefficients, so UC method may be applied, but you can also look at the form of the right-hand side. So e to power minus t over t. Yes, t appears on the denominator. So there is no homogeneous differential equation with constant coefficients whose solution contains the term 1 over t. Okay? So it is impossible to find an annihilator, or very difficult indeed. Good. So, but the method of variation of parameters may be used because there is no restriction on the type of non-homogeneity term. Okay? But what must be known? We have to know the two solutions of the corresponding homogeneous equation. So first consider the corresponding homogeneous equation. Which is an equation with constant coefficients, so no problem in finding with, let's write the characteristic equation promptly, immediately. Can you see that lambda squared plus 2 lambda plus 1 is the characteristic equation? Okay? So this is nothing but lambda plus 1 squared equal to 0. So lambda 1, 2 is minus 1, or minus 1 is a repeated root or a double root. Okay? So fundamental set of solutions. This is the third case where we have a double root or multiple root. So e to power minus t is a solution, and t times e to power minus t is another solution. Okay? Where, so that is y1 of t is e to power minus t, y2 of t is t times e to power minus t, are the two linearly independent solutions of the corresponding homogeneous equation. Okay? So with this, you can easily see that the homogeneous solution is C1 e to power minus t, C2 t e to power minus t. Okay? So by the method of variation of parameters, of course, to find the general solution, yes, we need also to find a particular solution. Therefore, by the method of, and we know the two solutions of the corresponding homogeneous system, so without any trouble, you may apply the method of variation of parameters. By the method of variation of parameters, we propose what we propose. We propose a solution like this: y1 of t, u1 of t, y2 of t, u2 of t in the second order case. So what we have, e to power minus t, u1 of t, plus t e to power minus t, u2 of t, where what is known, u1 prime and u2 prime are solutions of this system. y1, so let's write this system immediately. T e to power minus t, u1 prime, u2 prime. Good. I'm writing the fundamental matrix. E to power minus t is the derivative. And taking the derivative of that, we have 1 plus t, good, or 1 minus t, e to power minus t. So e to power minus t and minus t times e to power minus t. okay, is 0, and this is the right-hand side, e to power minus t over t. Okay? Not u1 and u2 in the proposed solution, but their derivatives can be determined from this system. Let's use again Cramer's rule. By Cramer's rule, let's find omega. What is omega? The determinant of the fundamental matrix or the coefficient matrix in this algebraic system in u1 prime, in the unknowns u1 prime and u2 prime. Okay? So what is it? 1 minus t e to power minus 2t plus t e to power minus 2t. Okay? So this term, and this term vanishes, I guess, and we get e to power minus 2t. Okay? As the determinant. So, look, this is nothing but the Wronskian determinant of the two solutions, and it is non-zero for all t. Is it surprising? No. If you look at the differential equation, the homogeneous differential equation, you will see that the coefficients are constants. So a solution exists throughout t interval from minus infinity up to infinity, okay, or exists for all t. So Wronskian determinant, okay, is non-zero for all t, or the two solutions are valid for all t. Two solutions of the corresponding homogeneous equation are valid for all t, or the solution of the corresponding homogeneous equation is valid for all t. Since the corresponding homogeneous equation is an equation with constant coefficients, and constants are defined everywhere, continuous everywhere. So existence uniqueness theorem tells us that for the homogeneous system, there exists a solution valid for all t. But the situation for the non-homogeneous equation is different, because the non-homogeneity term is undefined at t is equal to 0. So the solution of the non-homogeneous system is defined either for t interval from 0 to infinity, or t interval from minus infinity up to 0, excluding the point at the origin, t equal to 0. Right? So omega 1 is the determinant of what? 0 e to power minus t over t, t e to power minus t, 1 minus t e to power minus t, which is minus t and t cancel each other out. I'm taking the determinant, sorry, so use this determinant symbol. So we have e to power minus 2t with a minus sign. T and t cancel each other out. E to power minus t minus times e to power gives us this. Okay? And omega 2 is the determinant of this matrix, e to power minus t minus e to power minus t, 0 e to power minus t over t, which is now 1 over t e to power minus 2t. Correct? Okay, so by Cramer's rule, we find that u1 prime is omega 1 over omega. So omega 1 over omega gives minus e to power minus 2t over e to power minus 2t is minus 1, isn't it? Therefore, u1 of t is just integrating throughout is minus t plus some constant, but we can take that constant as 0 because we already know the homogeneous solution. If the constants, arbitrary integration constants are introduced, then we generate the general solution, including homogeneous solution as well. But since we are looking for a particular solution, let's take arbitrary integration constant 0. And what about u2 prime? u2 prime is omega 2 over omega, which is e to power minus 2t over t, e to power minus 2t, so 1 over t, correct? So I didn't memorize any formula, as you see. Just I know that we have to propose a particular solution of this type, in which y1 and y2 are known. And we have to know that not u1 and u2, we have to determine u1 and u2, but we have a system to determine first their derivatives. And this system is a system whose coefficient matrix is nothing but a fundamental matrix. Okay? Now, integrating that, we get u2, which is ln t. Okay? Or ln absolute value of t, which tell us that this solution involved ln t is valid when t is positive or when t is negative. Taking absolute value, it's okay. So I omit again the constant. So with this u1 and u2, particular solution is e to power minus t u1, so minus t e to power minus t plus u2 t e to power minus t, so t e to power minus t ln t. I choose this interval, t positive. Okay? So 2 interval, I am looking for a solution which is valid either in this interval or this interval. So I choose this interval, so I write ln t. So keeping in mind that ln t is defined when t is positive. So yp is of this form. Okay? So what is the general solution now? I get homogeneous solution. I get a particular solution. So the general solution is, so let's write the general solution here. Hence, the general solution suggested by the theory, general theory, is homogeneous solution is the superposition of a homogeneous solution and the particular solution. So it is of that form, C1 e to power minus t, C2 t e to power minus t, plus this non-homogeneous solution obtained by minus t e to power minus t plus t e to power minus t ln t for t positive. Okay? Now, in fact, you may say that this term in the particular solution may be incorporated with this term in the homogeneous solution. Therefore, the single form or the simpler form of a particular solution is just this one. Okay? Look, actually, we have C1 e to power C2 minus 1, t e to power minus t. Look, we define a new coefficient. As long as C2 is arbitrary, C2 minus 1 is also arbitrary. So this is a still homogeneous solution, plus the remaining part represents a particular solution. So yp with this, I say that perhaps the simpler form of a particular solution is t e to power minus t ln t. Okay? This part is incorporated with homogeneous term, with a solution which appears in the homogeneous equation. Okay. So, if there is a differential equation whose order is more than 2, of course, you have to solve a system of 3 equations in u1 prime, u2 prime, and u3 prime. And you have to know all the 3 independent solutions, y1, y2, and y3 of the corresponding homogeneous equation. Okay, another example, let us illustrate the fact that the variation of parameters may be used also for equations with variable coefficients. So here is such an example. For simplicity, again, I consider a second order ODE, okay? In order not to deal with a system, with a resulting system of 3 equations in 3 unknowns in the proposed particular solution, or in u1 prime, u2 prime, u3 prime, which are functions appearing in the particular solution. Example, another example. Let's find a good example from my notes. Okay, this is good enough. Here's an example. Consider the ODE. T square y double prime minus t plus 2 times y prime plus t plus 2 y is t cube. Okay? So, as you remember, do not forget, you have to consider the reduced form in order not to make any mistake. So, we have t plus 2 over t y prime plus t plus 2 over t squared y is t cubed over t squared, so t. So please be careful, f of t must be taken as t. Good? The right-hand side corresponding to the reduced form of the equation. So first of all, verify that somehow we get the two solutions of the corresponding homogeneous equation. Okay? First of all, verify that y1 of t, t and y2 of t, t times e to power t are two linearly independent solutions of the corresponding homogeneous equation valid either in this interval or in this interval. Again, as you see, the coefficients are undefined at the origin. So again, a solution is sure to exist for positive values of t or for strictly negative values of t. Good? Or in some t interval which does not contain the origin. And the largest possible t interval is either 0 infinity or minus infinity 0. Okay? Which is suggested by the general theory of linear ODEs. Okay? For simplicity, let us choose this interval, t positive, without any problem. So let us verify that, for example, y1 of t, for y1 of t, t, what is the derivative? 1. What is the second derivative? 0. So substitute into the homogeneous part. Okay? We have t squared 0 minus t, t plus 2, y prime is 1, plus t plus 2, t must be 0. Okay? I put this is y1, this is y1 prime, and this is y1 double prime. I substitute into the corresponding homogeneous equation, or you may use this homogeneous equation as well. So what is the result? Look, actually we have minus t squared minus 2t, so plus t squared plus 2t, which is indeed 0. Look, this and this cancel each other out, this and this cancel each other out. So y1, that is t, is a solution, okay, obtained somehow. Recall that there is in general no method to find solutions of a differential equation, even a linear differential operator, linear differential equation with variable coefficients. There is, unfortunately, no general method to solve a linear ODE with variable coefficients. In this specific example, we somehow guess that t is a solution and substitute into the homogeneous equation. So we see that it is satisfied. Similarly, for y2 equal to t e to power t, okay? I verify it. You may verify yourself that take the first derivative, second derivative, and substitute into the equation, homogeneous equation, okay? Not the non-homogeneous equation. You will see that this is indeed a solution. Okay, so part B Find a particular solution. So we have to use variation of parameters by the method variation of parameters. We propose what we propose this solution. T u1 of t. T e to power t u2 of t. Good. Let's write it as a particular solution. So when we integrate u1 prime and u2 prime, we take the arbitrary constants, arbitrary integration constants as 0. So what is known? u1 prime and u2 prime satisfies this system, where this system t e to power t, good, 1 plus t e to power t, where u1 prime and u2 prime satisfy simultaneously the system, which is very well known, u1 prime, u2 prime, 0 and f of t, but f of t is the non-homogeneity term corresponding to the reduced form of the ODE. So it is not t cube. Please be careful. It must be t. Okay? In general, this is 0 f of t. You recall? But f of t should come correctly if you take the reduced form of the equation. Okay? So by elimination or Cramer's rule, we find that omega, that is the determinant of the coefficient matrix, is what? 1 plus t e to power t minus t e to power t. So it is e to power t. T times e to power t cancel each other out, I guess. No. Isn't it? T1, t e to power t, so 1 plus t, and this, there is t here. Good, yeah. So t e to power t cancel each other out. So we have remaining t squared, isn't it? T squared e to power t remaining, yes? Okay, this is the Wronskian determinant, and as you see, this is non-zero. But non-zero for all t, is there any mistake? Okay. I expect that but it is non-zero for all t. So the coefficients are undefined at 0. And yes, it is 0, it is 0 when t is 0, okay? Which reflects the behavior of the singular structure of the coefficients at the origin. As you see, when t is 0, coefficients are undefined. So when t is 0, the Wronskian determinant is 0, which reflects the singularity at the origin. Okay, omega 1, what is omega 1? 0t, t e to power t, 1 plus t e to power t. So it is 1 plus t, t squared e to power t with a minus sign. And what about omega 2? Let's write it somewhere here. Omega 2 is this determinant, T1, 0, T. Good? So it is T squared. Yes? So with this omega 1, omega 2, by Cramer's rule, we find that U1 prime is omega 1 over omega, good, which is omega 1 over omega minus 1. Okay? Omega 1 divided by omega, and therefore U1 is minus T on integrating. I take integration constant as 0, okay? Because I'm interested in finding just a particular solution. I need not to find the homogeneous to reproduce the homogeneous equation or the solution of the homogeneous equation, because I know that it is the combination of this function and this function. Okay? So I need to find just a particular solution. So what is U2 prime? Omega 2 over omega. Omega 2 is T squared over that. We get T squared over T squared e to power T. So we have e to power minus T, isn't it? So U2 of T on integrating, you get minus e to power minus T plus some constant. Okay? So let's write down the solution. Where is YP? We propose. Yes, here is YP. Now, here is the form of a particular solution. It remains to put, now, we determine U1 and U2. So YP of T becomes T times U1, so minus T squared, good, or T times minus T plus T times e to power T, and U2, which is minus e to power minus T. Okay? So we have minus T squared plus or minus T e to power T times e to power minus T becomes unity. So we get that. Good? And I guess I suggest that a particular solution is minus T squared. Or it is the simplest or simpler form. Why? So this function may be incorporated with the homogeneous solution. Okay? Hence, what is the general solution? Y of t is C1t plus C2t e to power t minus t squared. So if you take minus t also in the particular solution, look, you can incorporate that term with this solution, okay? Which is unnecessary. So minus t squared is a particular solution. Actually, if you want, you can verify it, take its derivative and second derivative and substitute into the non-homogeneous equation. Please be careful. Yp is a solution which does not contain any arbitrary constant and which satisfies the non-homogeneous ODE upon substitution. Good? Therefore, if you want, you may prove that it satisfies this equation or this equation upon substitution.